So far we have discussed central atoms with 2 to 6 electron domains, and all of those electron domains are bonding domains. None of them is a lone pair or non-bonding. Now, let's say, for example, let's consider 4 electron domains, and 1 or 2 of them is non-bonding. So, before we do that, remember that for our previous discussion, the electron pair geometry is actually equal to the molecular geometry if and only if all of the bonding domains are, or all of the electron domains rather, are bonding domains. But if you have at least one lone pair, as we will consider for this slide, then the molecular geometry is not necessarily equal to the electron pair geometry. So let's say, for example, methane. So methane is something that we've considered earlier. Methane has 4 bonding pairs and no lone pairs. It has a tetrahedral electron pair geometry and still a tetrahedral molecule, or tetrahedral molecular geometry. The bond angles around VCH bonds are 109.5. Now, when you have ammonia, which has also 4 electron domains, but one of them is a lone pair, unlike methane, so as you can see for the structure of methane on the left, you have only these bonding pairs repelling each other. Okay, and there's another one, and then this one too, sure, and then this one and this one actually. Now, for ammonia, you still have those bonding pairs repelling each other. Okay, but now this time you have this extra lone pair, or you have that lone pair, which actually, again, occupies quite some space. It's trying to repel those 3 bonds as far as possible from itself as well. Now, as a result of all of those repulsions, again, the electron pair geometry of ammonia will be tetrahedral, but if we keep this out of sight, the lone pair, then it resembles a pyramid with a triangular base, which is basically trigonal pyramidal. So just a single pyramid with a triangular base. And notice that the difference between ammonia and methane as well is that the NH bonds in ammonia are actually at 107.5 degree angle apart from each other, whereas methane is 109.5. And the reason for that is, again, electron pair to bonding pair repulsions have a greater energy penalty, and in order to minimize those repulsions, we have to push back these NH bonds even further from the lone pair. Now, if you have water, we actually have a bonding angle here, or a bond angle between these two OH bonds of 104.5. And the reason for that is water, even though it has 4 electron domains, it actually has only 2 bonding pairs, and 2 of those electron domains are non-bonding or are lone pairs. And now, this time, not only do you have electron pair or lone pair rather to bonding pair repulsions, you also now have electron pair to electron pair repulsions. So again, lone pair to lone pair repulsions are actually much greater than lone pair to bonding pair repulsions. And as a result of that, these bonds have to be pushed in furthermore, and that explains the 104.5 degree angle. But now let's look at other structures in which you have 5 or 6 electron domains. If you have 5 electron domains, again, automatically the electron pair geometry is trigonal bipyramidal. If you have no lone pairs, like phosphorus pentafluoride, then the structure will be trigonal bipyramidal. The electron pair geometry is equal to the molecular geometry. Now, if you have, for example, sulfur tetrafluoride, notice, by the way, that all of these central atoms violate the octet rule. If you have sulfur tetrafluoride, you have 1 lone pair above sulfur, and for this, you now have a seesaw molecule, okay, if you don't consider this lone pair. Think of the seesaw here as basically this, and this is the stand of the seesaw. Okay, now for a trigonal bipyramidal molecule that's characterized by these bond angles. So this one's 90 degrees, okay, 90 degrees as well. This one is 120 degrees, okay, and then this one too will be 120, okay, and then this line here should be 180. Okay, now for a seesaw geometry, this bond angle should be less than 120 degrees, again because of this lone pair, which pushes those bonding pairs as far as possible from the lone pair. Oops, sorry. Okay, and then after that you have a T-shaped molecule. If this time, like chlorine trifluoride, you have 3 bonding pairs and 2 lone pairs. Okay, so you can see the T-shaped molecule is pretty flat, pretty planar. Okay, and if you have xenon difluoride, for example, in which you have 3 lone pairs and 2 bonding pairs only, still 5 electron domains, then you only have a linear molecule. So you can still see here from the position of those lone pairs that the electron pair geometry for xenon difluoride is still trigonal bipyramidal. That's the base of the pyramid, and then here's one pyramid basically. Not a great drawing, but you get the point, I hope. Okay, and then the other one will be something like that. Okay, I think that's just confusing. And then if you have 6 electron domains, as we have said earlier, if you have no lone pairs and all of those 6 electron domains are bonding, sorry, I thought I lost my pen, then you have an octahedral molecule. Okay, octahedral molecule, again characterized by 2 square pyramids pointing opposite each other. Now, one of those examples for an octahedral geometry or an octahedral geometry molecule will be sulfur hexafluoride. If you have a lone pair and 5 bonding pairs around the central atom, like bromine pentafluoride, then you have a square not square bipyramidal, but square pyramidal molecule. Again, that's only one square pyramid. Okay, so this is the base of the pyramid, and then you have that single pyramid only. Okay, and then if you have 4 bonding pairs and only 2 lone pairs, then you have a square planar molecule. Square planar molecule like xenon tetrafluoride looks like this, similar to the T-shaped and linear molecules above. A square planar molecule is actually flat in space. Okay, bond angles. So I think for T-shape that's obvious, 180 and 90. For linear, that's 180 and 180 only. For octahedral, so basically you have this as 180, and then this one will be 90 degrees. Okay, 90, 90, and then another 90. Okay, basically 90 times 4 will be 360, and these bond angles as well should be around 90, not exactly 90, because you now have a lone pair pushing those bonds out. Okay, so less than 90, I'll say. And then these square planar molecules, they're at 90 degrees from each other, but this one's 180 degrees. So for the test, it's important to actually memorize all of those angles. They're pretty much easy to remember, but I think one thing that you need to know first will be, again, what's the Lewis structure of the compound, and then after that, count how many electron domains you have. And then from the electron domains, know that usually if you have 4, 5, and 6 are what you will usually see. If you have 4 electron domains, you have a tetrahedral electron pair geometry, and count how many lone pairs. And from there, you can determine or predict what the molecular geometry is. Then 5 electron domains, will be trigonal bipyramidal electron geometry. And then 6 electron domains, that's